Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 8, Atomic Structure and Periodicity, Part 1. We are in Chapter 7 of your textbook. Here are our objectives for today. We're mostly going to be talking about waves and light and how we discuss those two things in the context of atomic structure. Pause here. You will only need a rough sketch of the picture. So you might be looking at this and wondering, is this really chemistry? This looks more like physics, and you wouldn't be totally wrong. But the reason why we're starting here is because atomic structure is really the way that electrons are situated and how they behave within the context of an atom or an ion. But because of the extremely small size of electrons, around 10 to the negative 31st kilograms, as compared to that of protons and neutrons, which is on the order of magnitude of 10 to the negative 27th kilograms, we have a very large difference in mass. And because of that extremely small mass of the electrons are oftentimes better described as waves as they are particles. That isn't always true, but it is true for a lot of different situations. So we're actually going to talk about properties of waves before we even really talk about electrons as waves. So what a wave is just a massless transfer of energy. When I think about wave, what makes it different from a particle isn't just its mass, but also the fact that waves don't have what's called definite location. Waves, they can be in more than one place at once. For example, when you see a light wave, you don't see localized photons, you just see light spread across the room. We describe waves by their wavelength, which is the distance between crests, crest being the top of the curve. That's typically measured in meters. The frequency, which is how often a crest will hit at a given point in time, we typically measure that in hertz, which is 1/seconds. And amplitude, which we're not going to talk as much about, but it is just the height of the wave. Amplitude you'll see more in like a physics class. Pause here, you don't need the picture. So now that we've discussed waves, we're going to talk about a specific type of wave, which is electromagnetic radiation, which is just energy released by electromagnetic processes. The way I think about it is electromagnetic radiation encapsulates any wave that is traveling at the speed of light. So that includes, but it is not limited to, visible light. It also includes microwaves, infrared radiation, ultraviolet, all that stuff. Pause here. So now we're going to mathematically relate wavelength, frequency, and the speed of light. This only works for things that are on the electromagnetic spectrum because they all travel at the speed of light. So the wavelength, we typically use what's called lambda to represent that, Lambda. Even though that looks like a V, that is actually a Greek letter I'm blanking on the name of right now. You can pretty much just use V for it, but it's for frequency. 1/seconds. And c is the speed of light. That is a constant. I would put that in your calculator. I have it in my calculator because I use it frequently enough, just 3.0 times 10 to the 8th. We're going to treat c like a constant, though, in terms of sig figs. Pause here. All right, I'll work through this. Right, so first off, I have to take 780 nanometers, and I have to convert it to meters. And then I can use lambda v equals c. I can rearrange this for v. Oh, I don't know why I just did 9 there. That was not intentional. Hopefully that didn't confuse you too much. And I got 3.8 times 10 to the 14th power, and that is in hertz. You could have also done 1/seconds. Or you could have also done seconds to the -1 power. It all just means the same thing. Pause here. So photons, we talk about electrons as being waves, but we can also take that reverse. We can take waves and describe them as particles. So let's just say I have a beam of light. Even though it is a wave, sometimes there are contexts in which we need to treat it as a particle. And when we do treat it as a particle, we will refer to it as a photon. That's what's called the dual nature of light. You could also think of it as the dual nature of matter as well, really the dual nature of everything. But if you need to know the energy of a photon, you take h, which is Planck's constant, 6.626 times 10 to the negative 34th power joules times seconds, and then multiply it by the frequency to get the energy. Let's take a look at this in action. Pause here, and I will work through this. We already have the frequency here, so all we have to do is plug this in. It wouldn't be a bad idea to put h in your calculator as well. I also have that in my calculator. And I got 2.5 times 10 to the negative 19th power, which is an order of magnitude that makes sense, and that is in joules. Thank you so much for watching and have a great night.